All these systems today, they have a somewhat different history, but today they all share the same principal technical setup, to large part running with shared code in between them. And web services is one important building block in how they work. So the history then. First use of web services was in the CPAM system about 15 years ago. And at that time, the system was running in VM. Then it was migrated to Windows, and then started using Dialog APL, using TCP socket, but still using custom functions built on the VM side and for handling HTTP, SOAP, and XML. A few years later, we started moving over to Conga, and yet another couple of years later, when the other two systems, Hercules and Mecca, were migrated also from VM to Windows, we started to move from using our own XML functions to make use of Quad XML. Some numbers on it. The way we use web services are both for making services available for other systems and for making services available for other parts of the application itself. So, for example, for Hercules and Mecca, we have an executable that is running as a fat client on the user PC. But for certain things that cannot be done in the local PC, we have web services on the server side making that functionality available. Similarly, for the CPAM system, we have a front end consisting of a web application, and the web application is then supported by the core CPAM system through web services. And so from the numbers, it's fairly obvious that the most intensive use of web services is in CPAM. So it looks a little closer of how that system is constructed. It looks somewhat like this. The end user is using the browser. Internet Explorer is the only browser within Volvo cars, basically. And the middle box here is the entire CPAM application running in one Windows server, but it basically consists of two parts. The left part, which is the web application, and the right part being the application server core application. And so the communication here now from other systems towards the CPAM core, as well as from the web application side, is done through web services. Some statistics, just to give an idea of how much the usage is. I took the log last week for 24 hours to see what the usage was, and during those 24 hours, 111 different services were used. In total, 36,000 requests, and it spreads out over the day with a peak during office hours. The absolute peak, 13 requests in a second. So fairly high amount, at least. And looking at how it breaks down, I mean, what's listed here are the different services and how much they were used. The names as such, of course, doesn't mean much, but as you can see, they are quite unevenly distributed. So, in effect, one service made up 2/3 of all the requests. This top 10 list also somewhat shows how the division between different users of services are, because the first top 3 there are for external systems that are not one of these APL systems. Then the middle 4 are for the web application, and the last 3 are for the Hercules application. So going then,
Peter, we can say about the 2 first. That means that if CPAM stops, there will be a hell of a cry in the company, because the second one is every. Will you say this?
Yes.
Oh, sorry. I thought you moved over.
So if we start looking at a simple example of how tightly interconnected our systems actually are with these services. This is a screenshot from the Hercules system, which is a Windows application, although it still looks like a VM application. What the screen here doesn't really matter, but on the left side there, what I've done is I've entered a code, an option code. And to get to the right side, what I've done is I've pressed enter. And when I press enter, I'm supposed to get the text description for that code. And the code there, the option code, as such, the Hercules system doesn't know what that is really. Because the Hercules system, for everything product structure related, it makes use of CPAM through web services. And so even such a simple thing as to look up the text for this, it has to go to CPAM. So if I run this in the debugger, the actual cutover point here is in a function calling query CPAM. And the way it's done then is that we send in 2 parameters, the first being the name of the service to use, and the second being the actual parameters to that service in XML format. And so the actual request being sent will then look like this, saying that I want to know what 000790 is. And also we pass along the end user name, so piece Simon 15 there, that is telling for traceability that it was me initiating this request. And then I get the result back with that text. And then the function making the call unpacks the XML and returns it in the format that we need it on the APL side. External systems then. We service a number of external systems. The 2 most important probably are these 2. The first one, ARO, is the factory ordering system at Volvo Cars. So they use CPAM services to check every single order being placed. And so if CPAM doesn't respond to this, basically, it will eventually stop the order flow and down the line cause a problem in the production. The other one is a global car configurator, which is basically a configuration engine for specifying a car, used both in the ordering system, but also in web-based configurators, such as the one you can use on volvocars.com website. And they use CPAM for a couple of different things. And they are the ones using that service that took up 2/3, as you saw in the first list there of the statistics. So that system is really the one actively pushing us to have a high availability, because of course if this system is unavailable, it might not immediately stop things, but it will make you look bad, so to say, in the eye of a customer perhaps. So a simple example of an external request This is from GC then a weight calculation where they send in an order specification. So all these numbers basically mean what kind of car, what engine, gearbox, and so on, what color, what upholstery, and what extra equipment is put on it. And then CPAM returns back how much does it weigh, what's the fuel consumption, what CO2 emissions, and so on. So to process these requests, we need some kind of load balancing, and the way we do that is by having a master process that receives the incoming requests, but then the actual processing of them are spread out on a number of slaves. And so master is responsible for listening on the public port. When a query is received, it is first checked to see if it's valid. If it's not, it is rejected with some kind of error return, invalid transaction, unauthorized. If it's okay, it's placed on queue, and then as soon as a slave becomes available, the next request on queue is passed on to that slave. The slave executes the query, returns the result to the master, which then returns the result to the requester on the kept open connection, and then closes the connection. And the way we set up it, we have the number of slaves is configurable, so we need to increase it. It's just a matter of updating a table, basically. All of it is running, both master and slaves are running as single-threaded processes using Dialog RT, and we start them up as Windows services using SRV any. Incoming port, the communication to the master is of course HTTP based, but between the master and the slaves we use the Conga command mode so that we can exchange the data in APL form rather than in XML. And to a large extent we also make use of keeping data in memory or in the workspace to speed up the handling of the requests. Access control is of course quite important because to some extent this is data that shouldn't be available just to anyone. So we have a handling for who should be able to use what services, and basically we keep for system, we keep a table of what system has what IP addresses, and then for each service who is allowed to use it. But then since we also use services for example the executable client for Hercules and Mecha systems, we need to be able to do it for a user that doesn't necessarily have a specific IP address. So there we use an authentication instead, which is based on IVA. We don't actually use the built-in one in Conga, but it's the same principle. And the reason why we don't use the built-in one is because we need to do it from Excel add-ins as well. As far as possible, we try to, of course, make the services execute quickly, short response times. But what we're handling here is quite complex data. In some cases, queries are not so easy to speed up. And also, sometimes we're treating a lot of data. So the transfer times are also a problem sometimes. to make sure that something simple, service that can be answered within 10th of a second or something, doesn't get blocked by a larger service that could take a couple of seconds, perhaps. We tie different services exclusively to some slaves, so that, for example, a time-consuming service may only run in slave 1, for example. That way, it will only block other long-time services, but quick services can execute in the other slaves. And another thing that we recently came across was that when we have a large arriving query, the DRC wait loop would keep returning all the blocks of that query rather than let any other small queries arriving through before it had completely processed that large request. So what we had to do was put in some strategy of doing some more specific wait calls to make sure that if we're processing a large incoming query and there's a new connection coming in to do something simple, we let that through.
Can you control that?
Yes, but what we actually done is to wait for the next connection with a 0 timeout.
Okay. All right.
What's the simple solution? And another thing is, of course, availability, where, as I said, we have some high demands on that from the external system making use of us. And we've had some problems recently, especially after having moved to virtual servers. So now there are talks going on that we maybe will be running this in a failover cluster. So if anyone has experience with running a dialog application in a Windows cluster, we're very interested in knowing more about that. And then a final thing, that sometimes this XML stuff is somewhat of an overhead, of course, both in that it inflates the data and that it adds processing time. So especially in between our own APL systems, we have in the last year started to move towards exchanging data in APL form instead, but still sticking to the same setup that we use for the proper XML-based web services. So in Hercules, for example, we even use the same master slaves to deliver both XML and APL-based services. Yes, that's what I had. Any one of you from the Volvo Cars side that would like to add something that I have forgotten, perhaps?
Yeah, that ready strategy, is that worth commenting on?
Yeah, I'm curious.
So mine.
I'm really puzzled on how you're doing it, because you're not allowed to wait on 2 levels in the same tree at 2 levels. But what you're doing, what are you doing to kind of just wait for a new connection without accepting data for one of the connections beneath that server?
What is it you're waiting on? Is it the server connection?
No, I mean the normal for in the loop receiving blocks. Wait, if you wait and you get a block, and you append that to some buffer, and then it goes back, wait again, get another block, and so on.
Yeah, for one of the connections.
No,
You're on the server side,
The basic wait is for everything.
right?
That is empty
On the
quotes.
listening.
Oh, yeah,
On
I
the
mean,
server socket.
listening on the whole thing.
Right.
And then you get block by block by block. And the problem is that if you do another wait, even if there is a new connection, that doesn't get reported by that wait until it has gotten the block lost.
Really?
Yeah, but how would you then get the connection, the new connection, without getting the next block?
So what we do is that we do wait for the name that will be on the next connection with a 0 timeout.
Oh, you're constructing the
Name would be
next
on the
consecutive number.
Yes.
So you're generating the next connection name and waiting for that with a 0 timeout.
Yes. And that will then immediately return that connection actually.
If it's
Hmm.
That's sneaky.
Yes, somewhat of a hack, I think,
Well,
but that was the only thing that we could
But is this
devise at that
is
time.
there a risk of doing this? Yeah.
no, not if you're doing it that way.
I mean, it's a risk, of course, if you would change the concept of how you construct the connection names.
Yeah, but I'm pretty predictable, you know.
Right. Okay.
I will leave out some prime numbers.
So 2 questions on that point. Are you receiving that big requests that you would have to do
And
this?
the reason why this came up as a big problem was that we introduced.
This thick cable is affecting this.
That we introduced a service to update data in the system, to publish data. And in that case, it can be quite large.
What size are we talking about?
10 to 20 megabytes or something. But the thing is that it originates from possibly a slow connection. So I don't know if that has any.
What is that the client? End?
Client end in that case is an Excel add-in.
Yeah, okay. So it is just a raw text connection.
Yes, it is.
And the next question is, of course,
Because
so
we don't have this problem, of course, with the command-based in any way. There you don't see this.
No, because in that case, I know exactly how much to receive. So I would receive it in Conga and then just pass it to APL when it's done. But when you're on a text connection or raw connection, every time I receive something, I would try to return it back to APL as soon as possible, because I have no idea whether I'm done or not done with the problem. And if you're on a slow connection and it's coming in very small chunks, you will get it maybe 5 bytes at the time, and you have to concatenate these 5 bytes to what you have received, and that would spend up a lot of APL time just doing that.
right. So how does Conga deal with this? If you get one incoming connection with 20 meg, and then immediately after is a 5 byte payload, will it process that one even if it hasn't received all the data? I thought it was just returning whatever it gets in.
Yeah, that is exactly what happens. I'm returning exactly what I get in. When I receive a chunk on the socket, I just pass that directly to APL. And maybe these chunks are obviously coming in small chunks, or maybe just because there's 10 megabytes, a lot of chunks.
Right, but do you not? I mean, does it stay on the first connection until it's completed before it's starting to pass on data from a second connection? I mean, why would he have to do this? I thought if you're just passing through whatever you get.
My suspicion is that all the chunks would be received pretty fast in Conga, because it's not taking me quite a long time to do that. And then a new connection arrives. But since I'm returning all the things I have received in order of
I see.
in the order that I received them,
Right.
all the small chunks would go first, and then eventually the new connection will come in last.
Right. So they're still being served in the right order that you received them.
Yeah, but there's just a lot of them.
Right.
Yeah, because if you run it in debug, you will see it spinning in the loop, basically.
I have heard that problem before, and we have some ideas on how to kind of amalgamate two buffers if they are received pretty close to each other. Or maybe you could set a timeout and say, I want, if anything received within 50 milliseconds, I should kind of glue together.
But this problem would go away if the HTTP stuff would be available in Conga, right?
If it's an HTTP request,
Yes, it is.
and you have set the content linked, yes.
But
If it is a I know, yeah, you just know how much.
It's chunked.
Yeah.
Right. I'd like to see this posted somewhere. It's a good trick. I didn't even know we could end up in that situation.
Yeah, it's very simple to emulate. You can do it on your own. I mean, just start a server and then start a client sending something.
Yeah.
And another one connect to it, and you will see that it will process the whole large data before accepting the new connection.
Right. Okay.
You could change your Redis strategy to one of the round robin ones, where you would take the first thing after on each connection, and then switch the connection to the one you handle last. I think it's Redis strategy 2 or something like that. But then you would not be sure that you would get your data in chronological order, but you would avoid this problem. And you could construct some cases where you would start some connections. Say they would handle very slow compared to other connections.
But isn't that what happens here? That the short request gets starved in favor?
Yeah, because if the large one takes maybe 10 seconds or something, and just as that started processing or started arriving, someone issues a short tenth of a second thing, they will have to wait 10 seconds rather than 1/10 of a second. So
in that case, you should probably choose the other Redis strategy, because you don't care too much about huge requests getting slowed down, where you favor kind of the small request.
yes,
And that one of the other strategies would favor that. How do you change that? You set it on the root. Set which Redis strategy you want to use.
What was it called? Ready strategy.
Yeah.
okay.
I need to read about that.
But isn't it, I think we have a discussion about this about email before, but isn't it so that the ready strategy only matters if you do several waits before you do send? That is, if
The Redis strategy controls how to.
no, if you do several sends before you do the wait. There was something, because we have a server sockets that really strong with wait. And then there's a request coming in command mode with Conga. And then the request comes in and we process it and we send it back out with send to that particular client. And we go into the loop and wait again and do the next request.
Yeah,
And I think we had a test case where we did a stress test and tried to see if Redis strategy made a difference.
Yeah, but as long as you're running in command mode, I know exactly how much to receive.
Yeah,
I will not pass it to you in chunks.
No.
Where they are kind of working in chunks and getting maybe in small chunks because it's a slow network. So they would be hit by that.
Okay.
But Peter, you don't have the content length.
No, but it wouldn't help.
I mean, we have the content length. We have, the first thing we read is the HTTP header, and there you have the content length. But I mean, Conga doesn't have the content length, so Conga will keep returning small pieces, and we need to glue them together.
Yeah, you cannot tell Conga to receive it all at once.
No, unfortunately not.
Not yet, at least.
No, but
Unless you have an end marker that you are sure of. You have that in a.
nope.
It's getting dodgy.
You just have the.
Content length of the HTTP header is all we have.
We should talk more about resolving.
Interesting.
Because this whole thing with chronological order, that's also, I think sometimes we would also be interested in not having that requirement. We talked about it before, about walking that data structure and trying to deduce the chronological, just call select on all sockets, and whatever is ready is when it's ready, and that you signal APL, and then when APL asks what's ready, you just pop them up in order. When they, like a global queue, it's DRC.wait, not handling different.
But then Peter would not be able to do his hack to get out of that.
No. You would not.
Yeah. That's another.
But then you would receive chunks in just the order in which you called select on all sockets, and then with that big case then.
Yeah, the chunks wouldn't drown out connection requests if you were just doing
I think the problem is that it's receiving the chunk is not a problem in the C layer, but returning them to APL becomes the time-consuming thing.
Yeah, I think so too.
Yeah, because now you have a data structure, you have a queue or a buffer per connection, and then you walk, when you call wait, you search among the connections to see which one should I return now.
Yeah.
But
and you always
my point, what if you have a global queue where everything that's completed just gets added, then as it's complete, then you wouldn't have to search the data structure.
No, but still you would have to have all the small chunks. You would have to go through all them before you.
Yeah, definitely. Yeah. He would still receive lots of chunks, but they would be interspersed with.
But I mean, another optimization we talked about is that if there is some data in a buffer and another piece arrives and it hasn't been picked up by APL, you just extend the buffer and it only becomes one event rather than being an event for every 5. I think that
would be really nice.
That would be really nice.
Yeah, but that is not extremely easy to do.
That's why we get paid, Jack.
I want to get paid more. You get more.
Sorry, are you getting paid by chunk?
Otherwise, I'm just everything in one go.
Right.
I have to make it look like something, you know.
Actually, I thought it was very interesting your structure with the servers and worker processes or slaves, as you call them, because we have, of course, the same issue that Dialog APL uses a single operating system thread, and how do you handle many connections?
Yeah.
And we did a similar thing, but we don't have a single front end, so we have lots of servers listening on lots of ports.
Yeah.
And then the client, since our client is APL as well, it just spreads out over different ports. And then we have different port ranges for example, potentially slow requests, just like you had specialized worker processes for potentially slow. So
we have that set up before.
Yeah, and that won't work, of course, if everything is over HTTP 48. So then you have to bond it out on the inside.
Yes.
Yeah, I was thinking Apache load balancing. If you know the services are using a specific URL, you could up the Apache and just distribute it. So it's redirecting it to an APL server on a specific port. So if you've got slaves 1 through 10 and you want to have that top service working on slaves 1 through 5 on the Apache configuration level, you could say any URL that starts with this service, pass it to these slaves.
But then you get, that's a good idea, and that's a very scalable idea, because then you can scale out Apache and put load balancers. But having a single queue like you do now is very efficient, because then as soon as any worker or slave is ready, it will take the next request. If you do what we do, because we have lots of processes and we didn't want coordination, you just distribute them, which you can do with Apache as well, or a HTTP load balancer. Then, of course, you get the issue that stochastically you get lots of requests coming to a single worker, and then they queue up. Or if you have a single request taking a long time, other requests might arrive after that. So you get worse latency, but better scalability in terms of number of processes. You don't have a single point of coordination like the master process.
Right. I can no longer see Denmark. I don't know what happened.
You can barely see Mel.
I'm not going home.
Did you turn on the
It's
light?
disappeared. Thank you very much.
There was